Okay, so let's change, uh, let's deviate somewhat from the frequency characteristics of a common source amplifier, and let's focus on the block diagram of our negative feedback loop, because ultimately we know that whatever amplifier, high gain amplifier we are making, will be putting it in a negative feedback loop, right? So it makes sense to understand why are we doing all these things if the context becomes clear. Okay, so let's clear the context of why we are interested in this frequency response of the of our amplifier, right? Okay, so what was let's go back to the block diagram of a negative feedback loop. So let's say this is the transfer forward gain A, and we have some structure like this. This is the structure that we were interested in, right? And then we saw that we had modified this structure and we came up with differential amplifier and so on. But still, this is the good old structure that can give us a lot of insight, right? So when we were developing this structure, we assumed that this guy is an amplifier without any capacitive effects, right? There were no capacitance, which means there was no frequency dependent effect. It didn't matter whether you are applying an input at 1 Hz or 1 gigahertz or 1 terahertz, the output we assumed would be unattenuated, right? But now we know that even though that is a wishful thinking, we will not be able to achieve, which means that we have to take into account what is the effect of the frequency, which means we have to take into account the effects of poles. Okay, so now this guy has some pole, so let's call this the gain or the transfer function at DC of this block is A0, and let's say we have pole 1 by S by P1, 1 plus S by P2, 2 poles, similar to the common source amplifier transfer function that we just did. Okay, so what will be the impact? So we can go around and do our analysis, right? So even before doing this analysis, what I would like to do is to give you an intuitive feel of why this becomes critical. Okay, so let's do that. So let's assume that this feedback is not on, right? So let's say this is broken, and this is how it is. And let's further assume that the input is a sinusoid of some frequency omega. Okay, so and let's assume the input sinusoid, so Vi is equal to Vp sine omega naught t, and let's assume omega naught is much less than P1 P2, right? So what will be V naught? If this is ideal voltage control voltage source, V naught will be A naught times Vi, right? So V naught will be some A naught times Vi. Okay, so if I have to sketch it in the same plot, right? So let's say this is A naught. So your Vi will be something like, our V naught will be, so I'm messing up my explanation, so let me try once again. So this is V input and this is V naught. Okay, so what will be the feedback voltage? 1 over K times V naught. So it may be a slightly attenuated version of V naught, right? So this is Vf. All good, right? So let's say we change the frequency. When you change the frequency, what's going to happen? Two things are going to happen. One, the amplitude of the output is going to reduce because the poles are going to kick in. Okay, and two, they are also going to shift in phase, right? They will not be aligned, right? The peaks will not align with a peak of the output, or the feedback voltage will not align with the peak of the input, right? So that's going to happen. So at non-zero omega naught, So at any arbitrary omega naught, right, maybe your input is something like this. So let me directly sketch the feedback voltage. Your feedback voltage might be something like this, right? It can be, right? So in other words, your input can be, if I have to draw it on the same scale, so our feedback voltage can be delayed with respect to the output. Okay. Okay, fine. So how much can it get delayed by? It can at max get delayed by 180 degree, right? But at the frequency at which it can get delayed by 180 degree, it is far away from, we have crossed both the poles, like we have left them long back behind, which means the amplitude will also be quite small, right? So essentially, if what will end up happening is, if so if let's say your at frequencies far higher than omega naught, much greater than T1 T2, right, if input is something like this, your output will probably be 180 degree delayed. So this will be something like this, but heavily attenuated, right? Okay, but let's assume there is another pole in the system, right? There is some additional delay in the system. Let's assume there is additional phase lag. What can be the source of additional phase lag? There can be additional pole. There can be an additional pole. So let's assume that there is an additional pole. Or even if we don't assume there is an additional pole, let's assume that there is an additional delay in the loop. So let's say there is additional delay, some TD. Right. So this delay can be because of an additional pole or something else, right? So let's assume we have an additional delay Vi. This is Vf. This is for now. This is 0. Okay. Okay. And the additional delay is such that assume there's an additional. So let me simply write it phase lag, right? Additional phase lag in the loop. Okay. Okay. Source can be an additional pole or something else. Okay. So what will this do? So let's assume that this is the case. What will this do? This will do one of these things, right? So for, let's say we had a certain frequency omega naught. So in the absence of delay, at some pole frequency, let's say Vf was or let's make a further one as assumption and assume omega naught is such that V naught j omega naught by Vi j omega naught, or rather, yeah, is equal to K. Okay. So this is under open loop condition, right? This is under open loop. Okay. Which means V naught j omega naught by Vf j omega naught by v I dot omega naught is equal to 1. Right? So in other words, let's assume we are operating at a frequency where loop gain, magnitude of the loop gain is equal to 1, right? So which means that uh, at omega naught, right, mod of L equal to 1. This is the assumption, right? This is assumed. So in the absence of this additional phase, we would have had some phase lag, right? But the key thing is that Vf would have been, the amplitude of the Vf would have been exactly as the amplitude of the input, right? Because we have by definition, we are operating at that frequency where the loop gain is 1. So maybe our loop gain Vf would have been something like this, right? So this is, let's assume this is in the absence of extra phase, right? But now let's assume we have added an extra phase. Okay, so if we have added an extra phase, and let's assume that this extra phase is such that it can delay it can delay Vf by that much amount, so that we get a total half cycle delay between input and output, right? So maybe I'll sketch it out so that will make more sense. So let's say in the presence of this extra phase delay, we get, this becomes the Vf. This is Vi. Correct? So let's assume this becomes Vf. Okay. So what's going to happen? So which means that here I have some sinusoid of some frequency omega, some omega naught. At Vf, I get kind of the same sinusoid, but it is inverted polarity, right? We have 180-degree phase shift, gain of 1. So essentially we get the same sinusoid with the inverted polarity. Okay, fine. Okay, so now what does this mean? As long as the loop is open, this doesn't mean anything. But let's do a thought experiment. A thought experiment is as follows. So let's assume further that we had a switch, right? We had a switch. This switch are complementary switches. At some time, let's assume this is phi and this is phi b, right? So complementary switches. So when phi is on, phi b is off. When phi b is on, phi is off. So right. So when the loop was broken, which means phi b was on and phi was off, right? This is what we are getting. Correct. So now let's say at some time t equal to t naught, at any arbitrary time you choose, I do the opposite. So I open phi b and I close phi. Okay. And also let's do one more thought experiment. Let's say that this is also phi b. Okay. So which means that at some time t naught, I am stopping the input, right? I am stopping the input and I am I'm connecting the feedback path in the loop, right? So assume that, so let me redraw it. This probably is getting a bit messier to understand. So let's say I am doing this. So at some time t, right? So this was grounded, this was open. Let's say this is at so this is at t equal to some ts minus. Okay, and let's say at t equal to ts plus, that is just after ts, what do? We ground the input and connect the feedback path here. What is going to happen? So let me remind you the fact that at t equal to ts minus, the input and the feedback voltages were identical in amplitude but 180 degree out of phase, right? So if we do this thought experiment, what's going to happen? So the feedback voltage will now appear at the input of the summer, right? So the feedback voltage here is this, right? Okay. So in the figure on the left, what was the error voltage? The error voltage was exactly equal to Vi, right? So this error voltage Ve was exactly equal to Vi because the feedback was turned off. In the figure on the right, what is going to be the VE? VE will be inverted of the feedback voltage, right? So VE will be inversion of the feedback voltage. Correct? Same amplitude, inverted feedback voltage, which means that from the perspective of the amplifier, its input hasn't changed, right? From the perspective of the amplifier, the input, even though you have taken the input out, even though Vi is 0, but the amplifier is still getting an input. VE is still that value, that sinusoid that would have appeared, right, even if the feedback were absent, right? Which means what? If the input of the amplifier, if the amplifier doesn't see any change at its input, the output will be exactly the same what it was earlier, correct? So what would have been the output? In this case, output is basically the inverted version of the input, right? Because amplitude is, in this case, k times amplitude and inverted version of the inverted in phase, right? So this, when seeps through to Vf, gets reduced in amplitude by a factor of k and becomes again equal to the amplitude of the proverbial input, which means that this becomes a self-sustaining loop, right? So this will be a self-sustaining loop or an oscillator. Okay, so your feedback loop can become an oscillator, right, if you get into this condition of loop gain, magnitude of the loop gain is equal to 1 and your phase is 180 degree, right? So in other words, what I'm trying to say is, this is something we for those of you who have taken control theory courses will know. So what is H? What is our V naught over Vi? V naught over Vi is some gain, ideally the gain of k by L by 1 plus L, right? So if, or in this case, L is a function of frequency. If L of j omega is equal to minus 1 for some omega equal to omega naught, right, then what do we see? We see that V naught over Vi goes to infinity, right? So this means that V naught over Vi tends to infinity, which means we have infinite loop gain. And infinite loop gain means what? Infinite loop gain means you don't need any finite output to get a finite input to get an output. The moment you turn on the system, the output will will be self-sustaining, right? And I just gave you an example of what might happen, right? So in this case, as you can see, at the frequency at which your omega at the frequency in which you have you satisfy this criteria of loop gain equal to 1 and the overall delay in the loop, overall phase in the loop is equal to 180 degree, then this loop can latch on to that particular frequency and you will keep on getting sinusoids of that particular frequency. Now you might say that, hey, if this were to be avoided, I simply won't apply any input at that frequency. In principle, it seems like true, but it's not actually practically feasible, because ultimately you have noise sources everywhere, right? And so there will be, even if you have not applied as explicit frequency, there will be frequency components in the circuit throughout the, I mean, because of noise, which is like broadband in nature. So you will have frequencies of all, you will have inputs of frequencies of inputs of all frequencies available in the network all the time, however small that might be, but it is only sufficient for the loop to latch on to any excitation at that frequency, right? The moment the loop finds that any excitation at the frequency which is bound to, it will start oscillating, right? So what we have to do, we have to steer clear of this condition of L of j omega to be equal to -1, right? So as you can now see, why is our why is the frequency response critical in a feedback loop, right? So our goal will be to stay sufficiently away from L j omega equal to -1 point, right? And this is what we will do in the remaining lectures in this course, right? Okay.